Thank you very much. And I start by thanking the organizers for the nice conference here and for the opportunity to speak here. And my work is, as you can read it, joint work with Jörg Feldvoss from the University of South Alabama. And we had some previous work on the cohomology of semi-simple Leibniz algebras, and this is kind of the follow-up where we consider nilpotent Leibniz algebras. Different field, but the same kind of questions. And so at first I should probably answer or explain the terms in the title. What is a Leibniz algebra? It is a vector space with a bracket such that the bracket acts as a derivation of itself. So I'm always talking about left Leibniz algebras. So this is the right identity, and Lode and Pirashvili, who are the fathers of this subject, and they always talk about right Leibniz algebra. So there may be some identities which cannot match up. You have to do some translation. Nilpotent is defined as for Lie algebras, yeah, and the vanishing theorems are about cohomology. Yeah, cohomology, and we had already talked about Lie algebra cohomology, and we have seen this morning in Noriaki Ikeda's talk the differential for Lie algebra cohomology. So let me just write down the co-chain spaces are exterior algebras, yeah, and in the Leibniz case, the co-chain spaces are based on tensor algebras or tensor spaces. Yeah, that's the main difference between Lie and Leibniz algebra. Yes. Sorry. Yes, yes. The tensor is bigger. No, I should not. Okay, I didn't want to do the historical speech. Yeah, so the historically speaking, in 1992, Jean-Louis Laude's observation was that the Chevalier-Eilenberg co-boundary operator can be lifted from the exterior powers to the tensor powers. This was kind of the starting point of Laude's interest in Leibniz algebras. Okay, so then what I also have to do is I have to tell to you why should we bother about Leibniz algebras? Why are Leibniz algebras interesting? And so one thing is Leibniz algebras arise in nature, yeah, in mathematics. We have already seen the derived bracket. Formalism. I think also in Noriaki Ikeda's talk, yeah. And so in general, when you do the derived bracket formalism, you don't get from a differential graded Lie algebra, another differential graded Lie algebra, but only Leibniz algebra. So in some sense, this is one source of Leibniz algebras, and another source of Leibniz algebras are courant algebroids, for which I can also refer to Noriaki Ikeda's talk, for example, but different people talked about courant algebroids. And so for a courant algebroid, you have two formulations of the bracket, one which is anti-symmetric but does not satisfy an interesting identity, and one which is not anti-symmetric but satisfies the Leibniz identity, and this is a Dorfman bracket, and so it's kind of naturally a Leibniz algebra. So that's only to say that Leibniz algebras do appear in mathematics naturally, and when I say Leibniz algebra here, I mean non-Lie Leibniz algebras, because Lie algebras are Leibniz algebras, but your hypothetical question would be, why bother about Leibniz algebras when we could always take them for Lie algebras? Okay. And in physics and field theory, so now I come to the situation of my subject with respect to the subject of the conference. It's unfortunately I'm an algebraist, or fortunately, so my subject is a little bit away from the main center of the conference, but Leibniz algebras appear even in gauge theory as symmetry algebras. For example, we have some work with Thomas on enhanced Leibniz algebras, which appear in non-abelian gauge theory. And the L-infinity algebras, which appear as symmetry algebras in physics theories, some of them can be obtained as from Leibniz algebras, and there Alexei Kotov, for example, and together with Thomas Strobel, have an interesting construction of an L-infinity algebra out of a Leibniz algebra, and the construction is based on the cohomology complex of the Leibniz algebra. So it's kind of intrinsically related to cohomology. So these few remarks just to tell you that cohomology of Leibniz algebras can be interesting even for you. Okay, this is kind of the overall motivation. And now the motivation of our work is are two theorems of Dixmier from 1955. And so they are kind of strange because cohomology for nilpotent Lie algebras is kind of dualistic. Either the module you're considering contains the trivial module, or it does not contain the trivial module. And if it does not contain the trivial module, if all the modules are trivial, then there's zero cohomology. And if it does contain the trivial module, then you have huge cohomology. And huge meaning you have at least dimension 1 for the extremal terms in degree 0 and degree the dimension of the Lie algebra, and in between you have even dimension greater or equal to 2. And so these are the theorems we would like to generalize to Leibniz algebras. And so the overall thing which turned out is the first theorem as a vanishing theorem generalizes rather easily to Leibniz algebras. But the second theorem, not at all. The second theorem, there's kind of a rupture and there are new phenomena appearing which we don't understand fully yet. So this is kind of the interesting theorem. Okay, but let me start by proving these theorems or reminding you how to prove these theorems. And so for the first theorem, I take the version of the proof from Donald-Barnes from 1967, which uses the Hochschild-Serre spectral sequence. So, using the Hochschild-Serre spectral sequence, you do a first step where you suppose the module is irreducible, and you do induction on the dimension of the Lie algebra. Yeah, so to initiate the induction, you need to consider the one-dimensional Lie algebra. And so what is cohomology of the one-dimensional Lie algebra with values in an arbitrary finite-dimensional module? And for this, we use, or Barnes uses a tool which we will see later on, which is the fitting decomposition. Yeah? The module decomposes into a fitting 0 component and a fitting 1 component. On the fitting 0 component, the generator of the one-dimensional Lie algebra acts nilpotently, and on the 1 component, it acts invertibly. Yeah? On the 0 component, as it acts nilpotently, yeah, if the invariants are 0, then the module must be 0, because by Engel's theorem, when you act nilpotently, yeah, you always have invariance. This is Engel's theorem. So, first of all, there exists an ideal of dimension 1. Why is that so? In every nilpotent Lie algebra, the center is non-trivial of the nilpotent Lie algebra, so pick an element of the center, that will do. That will do. Then the invariants under this one-dimensional ideal, they are included in M, and so by irreducibility, they are either equal to M or 0. Yeah? If they are 0, then by what I said before, here we have the cohomology of the one-dimensional Lie algebras with values in a module which does not have invariance. Yeah? So this means that the fitting 0 component is 0. Yeah? There's only the fitting 1 component. And the fitting 1 component, on the fitting 1 component, the generator of the one-dimensional Lie algebra acts invertibly. Yeah? So the quotient space M divided by what is generated by this one-dimensional Lie algebra is 0. Yeah? And this is the H1. The H0 is just the invariance here, which is also 0. And starting from degree 2 and so on, it's 0 because of dimension reasons. Yeah? So this means all of it is 0. So in the other case, when the invariants are M, then M will become a module over the quotient algebra. And here we can now apply the induction hypothesis. And this is 0 for all p greater or equal to 0. And now we have that in any case, this space is 0. Yeah? So this is clear for the first case. This is not so clear for the second case because we put another coefficient module here. But this is still the one-dimensional Lie algebra. So in this second case, this space will be either M or 0. Yeah? And so this suffices to say that this here implies that here. So in any case, this is 0, this HQ of the quotient algebra with values in HP of the one-dimensional value Lie algebra with values in M. And this is the E2 term of the Hochschild-Serre spectral sequence. And thus, if the E2 term is 0, all the cohomology is 0. This Hochschild-Serre spectral sequence converges to the cohomology of the Lie algebra G finitely. Yeah, so this is the first step, and the second step is very easy. It's just you have a composition series for your module and a long exact sequence in cohomology. So from the first step follows directly the result. Yeah, and so because of this second step, which is so easy, yeah, this is why vanishing results are easy, yeah, because they transmit according to long exact sequences, while non-vanishing results are not easy. They don't transmit according to long exact sequences. Yeah. Okay, this is the first Dixmier theorem, and let me prove to you also the second theorem. This is the non-vanishing theorem in case the module contains the trivial module. Yeah, and so in this case, we do the following. Yeah, first of all, a nilpotent Lie algebra does not only contain a one-dimensional ideal, also a codimension one ideal. Why is that so? Because the commutator algebra of the nilpotent Lie algebra cannot be all the nilpotent Lie algebra, otherwise it would be semi-simple. Yeah? So it must be strictly contained in it. Sorry? Perfect, thank you. Thank you. And so it should be strictly contained in it, and therefore you have just to choose codimension one subspace which contains the commutator subalgebra ideal, and this will be a codimension one ideal. Yeah, so always contains a codimension one ideal, and so there's one element in the Lie algebra which is not in this ideal, and so you have a direct sum decomposition of G as a vector space into this ideal plus k times x. Yeah, and what Dixmier does is he deduces from this a long exact sequence. Yeah, where these operators U, these maps U, are given by the action of x, yeah, the action by Lie derivative on the cohomology. And where does that come from? Actually, the long exact sequence comes from the short exact sequence of complexes, which is here. So you have the cochains on the Lie algebra. You can restrict them to the ideal, yeah? And this is because there's an injection of H into G. In the dual case, this gives an surjective map here, and there's some kernel. So this is a kernel complex, and the Dixmier's work was to understand this kernel complex. This kernel complex here is relatively easy because cochains are exterior products. So to be in the kernel means for the cochain that there's one factor which you can put in the first spot, which is in kx here. Yeah, here in this exterior product, there's one factor kx, and then come factors in h. And so this kernel complex is isomorphic already as a vector space to Ci minus 1 of h, yeah, just taking out this first factor, or saying it differently, putting in x, yeah, with the insertion operator ix, and then restricting, this is res here, restricting to the codimension one ideal. Yeah, so that is a map which is an isomorphism of vector spaces. And the first thing to note is that this maps is compatible with differentials. Yeah, and it is compatible with differentials because of Cartan's formula. Because when you put here d f tilde, yeah, then Ix df tilde. By Cartan's formula, you can put the d on the other side, modulo 1 Lx, yeah, but you can see right away that res Lx of f is 0, yeah, because you didn't when you do Lx, you don't kill the x component, yeah. You don't kill the x component. You have to kill the x component in order to have something non-zero when you restrict to the subalgebra. Yeah? And so this makes it a morphism of complexes. This is the first step. This identifies this term here with h minus 1 hm. Maybe I could take this out. And the second step is that you ask about the connecting homomorphism, yeah, which is here, yeah, goes from HIH to HI plus 1 of this kernel complex, but this we identified with yeah, CI of HM. And so the connecting homomorphism, what does it do? It takes a cochain from the complex of the codimension 1 ideal, lifts it to the whole Lie algebra. This is this lifting is the tilde, C tilde, and then you do D, yeah, and this the D of this lifting lives in the leftmost term. Yeah, this is the connecting homomorphism. And so here, once again, you can do the Cartan formula game. And when you compose the connecting homomorphism with this map here, yeah, then you get this map here. And up to a co-boundary, yeah, because of Cartan's formula, this is just that. Now this Lie derivative here is not 0 anymore, yeah, because yeah, and so yes, so this is this proposition, yeah, and this is the main proposition which helps us in the proof, because now let us suppose that all x on G act nilpotently on M, and here once again we use the fitting decomposition. Our module is the direct sum of, yeah, actually this is what we will see later on, that the fitting 1 decomposition never contributes to cohomology, yeah, but this we will see later on. So we can suppose that it acts nilpotently, and we reason by induction on G. These endomorphisms UI and UI minus 1 are nilpotent, yeah, because they are given by Lx, and these X acts nilpotently on everything. And so, yeah, then I just wrote down the proof for these middle terms where the dimension is greater or equal to 2. Yeah, maybe you can figure out yourself the proofs for the edge terms, which are where the dimension is only greater or equal to 1. This is included in there. Yeah, so for these middle terms, we have that these two terms here are non-zero, but UI is nilpotent, so the kernel is non-zero. Kernel non-zero means that this map here is non-zero, and the image cannot be the whole space because of nilpotency, and so this map here cannot be 0, and so Ri is 0 with non-trivial kernel, and this means by the rank theorem that this is greater or equal to 2. Yeah, so this is these are the two Dixmier theorems. Okay, now let's come to the Leibniz world. And in the Leibniz world, there the natural modules are bimodules. Yeah, you always have an operation from the right and from the left. And these operations, I denote them by lambda and rho. Lambda like left and rho like right. And in order to be such a Leibniz bimodule, there are three axioms, yeah, how they have to be compatible with the bracket, and these are written here. And for example, just to tell you how this, how one deals with these, when you take the sum of the second two relations, then you find that x dot m plus m dot x, the whole thing dotted by y from the right is 0. Yeah. And so when you have just the first identity here, you say that M is like a Lie module because you have only left operation which satisfies the axioms of a Lie module, or what is equivalent a module over the quotient Lie algebra. Yeah, I didn't tell you about the ideal of squares. Maybe I should say this. In every Leibniz algebra, now you have unusual things. Yeah, you have what is called the squares or the Leibniz ideal of the Leibniz algebra G Leibniz, which is the vector space generated by the squares. Yeah, and so the quotient is then a Lie algebra. Yeah, and so being a Lie module means also being a module over this quotient Lie algebra. And so from this identity, what do we get? When you have just a Lie module, you can see it as a Leibniz module in two ways. Yeah, you can either, when you have a Lie module, you just have the left operation, and you can say that the right operation is 0. Then you call it an anti-symmetric bimodule. Or you can say that the right operation is minus the left operation, and then you call it a symmetric bimodule. And so when you do the sum of these two, this implies that this subspace generated by the sums of these two expressions is an anti-symmetric and even a sub-bimodule. Yeah? And so we have, for example, this kind of short exact sequence for every bimodule. Yeah? Every bimodule has this anti-symmetric sub-bimodule such that the quotient bimodule is in fact symmetric. Yeah? And so in this category of Leibniz bimodules, every object is this kind of extension of an antisymmetric and a symmetric bimodule. Okay, just to talk a little bit about bimodules and to introduce to you this M0. But now, I already pronounced several times the word fitting decomposition. So what is a fitting decomposition? Maybe you know this already. When you have a vector space and an endomorphism, first of all, we say that this endomorphism acts locally nilpotently on the vector space if for every vector there is an integer such that this is 0. So now the fitting decomposition, yeah, for an endomorphism on a finite-dimensional vector space is a direct sum decomposition of V into V0 and V1. which are defined here, yeah, and so the whole game here, in order to show that they are stable subspaces, that T acts nilpotently on the one and invertibly on the other, all this relies on the fact that these unions and this union and this intersection stabilizes, yeah, and it stabilizes because the vector space is finite dimensional. So there is a T such that V0 of T is equal to kernel of T to the small t, yeah, and so from there you can show all these properties, which are very well done in Jacobson's book on the algebras. Okay. So the first thing we did with Jörg was generalize or introduce, if you want to, the fitting decomposition of a Leibniz bimodule. Yeah? And it's kind of clear how to do this if you have now not just one endomorphism, but a whole bunch of endomorphisms, a subset, yeah? Then you take for the zero space the intersection, and for the one space the sum, yeah? And taking the sum here blows off the possibility that S acts invertibly on this M1 of S, yeah? So you don't, this is the only property you lose. But all the other properties, the fact that it is a direct sum, that it works, that the both are sub bimodules, and that it works, it acts nilpotently on the first component. All this you still have, yeah. And so. Okay, this is kind of very much expected, and the only thing here is that we have a formula which is very well known, which gets you from the left operation to the right operation. So if it's nilpotent from the left operation, it's already nilpotent from the right operation, yeah, and you can write down by induction formulas for this, which show this theorem very easily. This is not very deep. This is just adaptation of this fitting decomposition to the framework of bimodules. Yeah. Maybe you ask yourself, why do we need that the dimension is finite only for the last two ones? The stabilization of these subspaces of these kernels and the images, yeah, you only need it, for example, for the direct sum, or here for M1, yeah, M0. Even if even if I think it was the intersection of the kernels, was it? No, it was, yeah, sorry. Was the union of the kernels. If the union of the kernels does not stabilize, yeah, it's not very important for A and B, yeah. So, but it is important for D, for example, yeah. This is why we formulated it in this way. Okay. So these are preliminary things, and now let's go into the cohomology vanishing. And here we, yes, here first of all I should say, I showed you the Dixmier theorem using the Hochschild-Serre spectral sequence, yeah. And already in our first paper with Jörg, we or what is very well known since Pirashvili's spectral sequences is that the Hochschild-Serre spectral sequence does not work, or works very weakly only for Leibniz algebras. Yeah, so this proof was totally out. So we had to do something else. And so as Jörg Feldvoss is student of Helmut Strade and Rolf Farnsteiner also, Jörg knows very well the work also of Rolf Farnsteiner, and he knew that Farnsteiner did some work on these cohomology vanishing theorems. And so what we did was we adapt this method of Farnsteiner to our setting. Yeah, and so the first lemma we just took from Farnsteiner, but it's kind of disturbing. Yes, this is why I wanted to show it to you too. You take two left G models. Yeah, G will be always now a Leibniz algebra, and M will always be a Leibniz G bimodule, yeah, and both of them are mostly considered to be finite dimensional. And I told you that left modules means then that it's only this first condition LLM is supposed to be valid. Yeah, we need only this. Yeah. So suppose there exists an element which acts locally nilpotently on the V and invertibly on the W, then acts invertibly on the Hom space. Yeah, this is kind of very strange, but true. And so how does Farnsteiner prove this? He introduces this alpha phi, yeah, for any map from any linear map phi from W to W, which is the sandwiching of F between this left action on V by X and action here on the W by phi on the outside. And the key thing is that because it acts locally nilpotently, this infinite sum exists as a homomorphism, yeah? On each single vector V, it makes sense, yeah? On each single vector V, it is a finite sum and makes sense, and it is a homomorphism. And such, and thus we can do the telescopic sum trick, yeah, and we get that identity minus alpha phi is invertible with this inverse, and then also this gamma, yeah, which is on the one hand this here, which we have shown to be invertible, composed with the left multiplication by the lambda x on W, yeah, the action on this W. This is also invertible, yeah, because it's a composition of two invertible things, and it gives exactly the action on the Hom space which we want. Yeah? And so this is kind of the heart of all cohomology vanishing theorems, because now when we apply this to the cohomology complex here, yeah, and we have that at acts locally nilpotently on G and lambda, and there is an element A which acts invertibly on the module, then by the previous lemma, we can show that the Lie algebra acts invertibly on yes. Yeah, maybe I should not say that G acts invertibly on this, but what was it? Yeah, A acts invertibly on this complex here, yeah, on the whole complex, and the action is compatible by the Cartan formula. It's compatible with the differential, so it acts invertibly on the cohomology, yeah. But on the other hand, the Cartan relation tells you that the Lie algebra always acts trivially on the cohomology. Thus, the cohomology must be trivial. Yeah? So this is always the reasoning. And now we can envelop it in different ways. Yeah, but this is kind of the heart of it. Now we take in the fitting decomposition. In case the dimension of M over the zero fitting composition with respect to some subset S of G is finite dimensional, yeah, we can show that only the zero component of the fitting decomposition is important for the cohomology, yeah, because you can do induction on this finite dimension here. If it's 0, then the M1 space is already 0. If it's greater than 0, then there exists an element S, 0 in S, which is such that M0 of lambda S0 is not equal to M. And this N is again a bimodule of M. One has to show this. And one has to show that they have the same zero components. But this is also very elementary, yeah. But let me skip this in order not to make too many details. Then we can apply induction hypothesis to N and have that the cohomology is only given by the zero component, but the zero component is also the zero component of M. Yeah? And then we use the long exact sequence according to the short exact sequence, and we have that the cohomology on the quotient space is 0 because lambda S0 acts invertibly on the quotient space. Yeah, and this is again the lemma from the beginning. Okay. So as a corollary, we can show that when we have a Leibniz algebra with a nilpotent ideal and a finite dimensional Leibniz G bimodule, such that the invariants of the bimodule, the right invariants, are 0, then all the cohomology is 0. Because, yeah, this is the case because if the M0 of N would be non-zero, yeah, then this would act nilpotently on this space. And by this is then the reasoning which I already used. By Engel's theorem, we have an invariant vector, a non-zero invariant vector, yeah, and this is a contradiction. Yeah. Okay, yeah. So here I stopped the very detailed explanation of our theorems with some more work, but which is not more complicated than what we did here. It's just a question of time. We arrive at a almost complete analogon to Dixmier's theorem. Meaning if you have G and M finite dimensional, if every composition factor of M in M is non-trivial, then the cohomology is 0, but we have to fiddle around with a degree 0 case. Yeah, in degree 0 you can have cohomology. For example, for an antisymmetric module, the H0 is always the module. Yeah, so we cannot have full Dixmier theorem, but this is kind of the closest we can get to Dixmier's theorem, yeah, and it's true. Okay, this is kind of the nice, smooth, easy story. Now comes the rough, not so easy story, the non-vanishing theorems. First of all, the proof of Dixmier on this non-vanishing theorem goes by induction on the dimension of the algebra. Yeah? So in order to do any kind of induction, one has to think about the one-dimensional Lie or Leibniz algebra. Yeah? So what can we say about the cohomology of the one-dimensional Lie Leibniz algebra with values in any finite-dimensional bimodule. And this is what we can say. Actually, we were very much surprised. Yeah, the degree zero case is always kind of a different story. Yeah, but starting from degree zero, it becomes periodic. Yeah, in odd degree we have these spaces, and in even degree we have that spaces. Okay, mg is the right invariance. Maybe I should write down these spaces. Oh yeah, the m lower zero is this one. M upper G is the right invariance, and which one do I, yeah, this product there is what is generated by the, oh no, here, sorry. What is generated by the right action, by the right operation, I should say, yeah. So, yeah, it turned out to be periodic. And if the bimodule is finite dimensional, it's even, yeah, it's even in degree zero we have something, and then starting from degree zero we have always the same space. And so I told this to my friend and colleague Geoffrey Powell in Angers, and he thought a little bit about it and said, oh yes, this I understand why it is periodic, yeah. And he told us the universal enveloping, the Leibniz enveloping algebra of this Leibniz algebra is isomorphic to this infinite dimensional associative commutative algebra. Yeah, this is also already in a paper by Lode. But the bimodule, yeah, which is here, which is the universal enveloping algebra of the quotient Lie algebra, yeah, which is just the algebra itself, has a periodic resolution. Yeah, and so what is this periodic resolution? Yeah, it's a resolution of k of x, and the first term you write down is this quotient here, and the kernel is k of y. Okay, this Leibniz enveloping algebra is generated by the lambda x and rho x, with small x being in the Leibniz algebra. Yeah, and so here for the one-dimensional Leibniz algebra, we have one generator lambda E. Let's say E is the generator of the one-dimensional Leibniz algebra, and one generator X, which is rho of E. Yeah, and so these are the X and Y. And when you write down the equations, the three equations, LLM, LML, and MLL, then you get finally that the only relation is that XY is 0. Yeah? And that it is commutative, sorry. And so you get as the enveloping algebra in the Leibniz sense, this algebra here, and Kx has a periodic resolution because you have a natural map from this quotient space to Kx, yeah, and the kernel is Ky. Yeah, okay, you have to fiddle around a little bit maybe in order to see this, and then it goes on. Yeah, the kernel you can have a natural map from the quotient space to Ky, and the kernel is Kx. Yeah, and so it switches between Kx and Ky, and so it gets a periodic resolution, and this explains why the cohomology is periodic, because the cohomology is just an ext. Yeah, I'm sorry here I omitted parenthesis. Yeah, it's the ext, the usual ext functor over this associative algebra, where in the first component you always write this module, yeah, and in the second component you write the arbitrary module you want to compute the cohomology of. And so if this first module has a periodic resolution, the cohomology always is periodic. Yeah? And so this is kind of very interesting, I believe, because this led us to the question, which Leibniz algebras have this property, the property that UG Lie has a periodic resolution. Yeah? If you can say this, then for these Leibniz algebras, you can compute cohomology very easily. You only have to compute the first, yeah, let's say 2 or 3 spaces, and then it goes on like this always. Yeah, this is kind of sorry? You can ask the question for any Lie algebra. We are kind of in the framework of nilpotent Lie algebras, but you can ask the question for any Leibniz algebra. And in some sense, this is a phenomenon which we already observed, that very often Leibniz cohomology is much more regular than Lie cohomology. Yeah, Lie cohomology has to stop after the dimension and does some things inverse. But while Leibniz cohomology is somehow, you have some things and then it goes on like this to infinity. Yeah, and so we believe that this is encoded in this periodicity question. Maybe actually I should have said this earlier. Actually, I wanted to give you an example of non-Lie Leibniz algebra, yeah, earlier than that. So let's take this 2-dimensional nilpotent Leibniz non-Lie algebra N, which is generated by 2 generators, E and F, with the only bracket F is E. Yeah, this is kind of a very nice example of a Leibniz algebra, which is non-Lie, because it's kind of a central extension of the abelian 1-dimensional Lie or Leibniz algebra, but central extension by a symmetric cocycle. Yeah, while Heisenberg would be anti-symmetric, etc. But you can always do the same thing as Heisenberg in the symmetric setting. And we computed for this Leibniz algebra that it also has a periodic resolution, and so by this we can also determine all of its cohomology. Okay, but this is unfortunately all I can say about this. I tried to see whether, for example, all Lie algebras seen as Leibniz algebras have this property, or all nilpotent Lie algebras, or all nilpotent Leibniz algebras, or something. For the moment, I don't have any idea, any clue how this could work. Yeah. So my last 5 minutes I spent on the non-vanishing theorem. For the moment, I only talked about the 1-dimensional Leibniz algebra. These quotient spaces we had before, these quotient spaces, first of all, we thought that they are always non-zero, but no. They actually, for this Leibniz algebra N, for the adjoint action, these quotient spaces are zero. Yeah, so we have an example of a two-dimensional Leibniz non-Lie algebra such that the cohomology after degree 0 is 0 all the times. Yeah, so this is kind of very strange for Dixmier, yeah, because in Dixmier the adjoint representation always contains the trivial module, yeah, because of the center of a nilpotent Leibniz algebra, which must be non-zero. And so from Dixmier's point of view, this cohomology should be non-zero, but no, it is 0. Yeah, and so this led us then to the theorem which is down here. In case these quotient spaces, yeah, are non-zero, we can put them into the induction, yeah, and get by induction non-zero spaces all along with an argument very, very close to Dixmier's argument. Yeah. Here there should be nilpotent. G should be nilpotent. Yeah, I'm sorry. Yeah, I'm sorry. I was letting out all these recurrent hypotheses on G and on M, but you're right. This should be emphasized. Yeah, G is nilpotent here. Let G be a nilpotent finite-dimensional Leibniz algebra. Yeah, and M a finite-dimensional Leibniz G bimodule, such that these quotient spaces are, this quotient space is non-zero, then we have non-vanishing cohomology. Yeah, and so just in order to tell you why this is much more complicated than in the Dixmier case, I told you in the Dixmier case, the quotient complex, the kernel complex has just one factor kx at one point in this Hom space. Yeah, but in the Leibniz setting, this factor kx can now be at, first of all, at any place, because it's not an exterior algebra anymore. Yeah, you cannot push it around, and you can have several of it. Yeah, and all these are in the kernel of the restriction map. Yeah, all this whole thing here, where the kx is at any place here, can be in the kernel, and you can even have all of the tensor factors equal to kx. Yeah, and so it gets much more complicated to reason with this big kernel complex. Yeah, but nevertheless we can show this theorem. Okay, I think this is all I wanted to say. Oh no, I have some remarks. Yeah, first of all, the trivial module always satisfies this hypothesis. So for trivial coefficients, we always have cohomology non-vanishing cohomology. And for the adjoint module, it's much more, yeah, it depends, because when you translate what these spaces mg and m0 and so on are, it is the left center divided by the Leibniz ideal, by the ideal of squares. Yeah? If the left center is equal to the ideal of squares, then the quotient space is 0. Yeah? And so we cannot say anything. But if it's not, then the quotient space is non-zero, and we have our non-vanishing theorem. Yeah? And so Akrom Omirov asked me, how many, maybe 5 years ago, 6 years ago, whether a finite-dimensional nilpotent Leibniz algebra always has an exterior derivation. Yeah, this is a very classical question for Lie algebras, and for Lie algebras it is true. And one has to say a name with it. Help me, Dietrich. Dixmier conjecture, or Dixmier result, or Dixmier something. Okay. Jacob, yeah, I always, okay. Let's say Jacobs and Dixmier and cover it up. Okay, and Bakrom Omirov asked me this question for Leibniz algebras. Is it true? And so the answer is no. Actually, it is not true, and we have counterexamples. Yeah. Okay, this is what I wanted to say, and I thank you for listening to it.